All right, we've looked at some of the benefits and some of the pitfalls of AV over IP. Now it's time to actually dive into the practicalities of how do we actually do this stuff? How do we transfer pixels across our network? So there are lots of AV over IP standards. And in fact, Brompton has been doing AV over networks for over a decade. Our own Tessera protocol is specifically designed to operate between our processors and between LED panels over an Ethernet network. But it's highly optimized for LED screens. So it's not entirely appropriate. It's also not IP-based. So there are other standards that are better suited to interconnecting between video devices. And there's a huge number of standards to choose from, and we're not going to talk about all of them. The ones that we are particularly interested in are ST2110, which is primarily broadcast focused, but is now being adopted elsewhere. We're going to talk about NMOS, which is very closely related to ST2110 and is more about how you manage a 2110 system. And we're going to talk about IPMX, which sits on top of both of them to improve the end user experience, to improve interoperability. So let's start with SMPTE 2110. And 2110 is the conceptual successor to SDI. So SDI essentially takes us as far as 4K over a piece of coax cable, but at the point where we want to go beyond that, the bandwidth rapidly ramps up, and continuing down that route makes it much more difficult to actually run the signal over long distances, and it also would realistically get expensive compared to transitioning to IP. So SMPTE, who created the standard, have looked at this and said, okay, it's time to transition to IP. And to that end, they have created a suite of standards within the 2110 umbrella, and there are quite a lot of them. So 2110-10 is all about system timing, -20 is uncompressed video, -21 talks about the timing for video, and so on. Now, some of these standards we're more interested in than others. The audio one I'm going to pick on because, again, that's not something particularly relevant to us in terms of LED screens. But there is this entire suite of standards. And the one at the bottom is just worth mentioning as well. 2110 references the 2022-7 standard to be able to do redundancy. And we're going to look at that just briefly a little bit later on. So, to recap, we've already said AV is essentially three things: data, timing, and a shared interpretation. So we need to take our data and our timing, and we need to send these over our IP network. We also need to look at our shared interpretation, which you'll recall potentially might have come from something like an HDMI standard or a DisplayPort standard. Well, those aren't appropriate here. So we are going to have to extend our interpretation so that it works over IP. So let's take these in turn. Let's start with the data, which in our case is very much video data and how we send that over IP. So data, you'll recall, is a stream of pixels in a known format, encoded in a particular order. So this is a continuous stream of data, essentially. But if we're going to transmit it over an IP network, because we're working with a packet switch network, we are going to have to divide up that data into easy-to-handle chunks. So we take a number of pixels, and we are going to put them into a packet. We'll take some more pixels, put them in the next packet, and we're going to repeat that to generate a whole stream of packets that we want to send. The exact details of how this works are specified as part of the SMPTE 2110-20 standard, and it goes into lots of detail about taking pixels and combining them into P groups and the exact nuances of how we need to pack that data into the packets. We don't need to worry about that level of data, fortunately. We just need to understand that that video data is being packetized into this series of packets that we're going to want to send. Now, I said I'm not going to talk too much about anything that's not video here, but it is worth just talking briefly to understand that actually for other types of data, and this might be audio, for example, that we want to send over IP, that data is going to be processed in a similar way, but separately. So again, in the case of audio, perhaps we're going to take a whole series of audio samples, and those are going to be put into a single packet, ready to send over the network. So similar to what we do with video, but separate. And it's helpful that it's separate because it means that as a video receiver, if we're not interested in the audio data, we can just ignore that stream and focus on the video stream. 2110 uses an existing protocol to be able to then pack this data into packets. It uses RTP, or Real-Time Transport Protocol. And that defines the exact details of how we take those pixels, how we wrap them up to send them within a packet, so that we can send it over our IP network. But it is important to bear in mind that that process is taking the video data and wrapping it and sending that as one stream, and then entirely separately, any other types of data, be it audio, ancillary data, those are handled as separate streams. So we need to address those streams, and we're going to take a single type of data, so some pixels, for example, and that's going to form the data that we want to send within our packet. We then need to decide where we are going to transmit that data. And we're going to add a destination IP address and a port. So we know not only which device we are sending the data to, but also it knows how to interpret it. Which video stream does this data need to be considered part of? We can transmit it over the network using unicast, if we're only transmitting to a single receiver. Don't want to use broadcast, as we talked about before, because everybody would get overwhelmed, but it's also okay to use multicast if we want to send the traffic to multiple receivers, each of which then will receive an identical copy of that video stream. So great, we've added our destination IP address and our port. We're ready to send that packet. But when are we supposed to be sending that packet? And indeed, when are we supposed to be sending all of the other packets that are going to form that video stream? Packet scheduling is a really important part of SMPTE 2110. And I'm just going to talk a little bit about why that is. So there's various ways that we could do this that's not going to end well. So the most obvious one is that we decide that we're going to send our packets at the maximum rate that our connection will support. And if we do that, we're just sending packets back to back as fast as you possibly can. And a good analogy perhaps here is to say that you're a bit thirsty, you want a drink, so you're going to grab a fire hose and try and drink from it. Well, you're probably going to get a drink, but you're also going to get a little bit more than you bargained for, and ultimately you're going to drop quite a lot of that water, you're going to drop a load of packets. It's not going to be very successful. So let's not send at the maximum possible rate that we can. Let's also be careful that even if we're backing off the average rate that we're transmitting at, we need to be very careful sending data in a very bursty fashion. And by bursty, I essentially mean that we would send out lots of packets back to back, and then there'd be a bit of a pause, and then we'll send lots of packets back to back again. And the equivalent here would be saying, well, we're still a bit thirsty, we're not going to use the fire hose this time, we're going to try a bucket of water and see how well that goes. Again, probably not going to give you what you want. Okay. So really what we need to do is we need to send packets at nice, regular intervals. And if we do that and we space out the data as it's going across the network, that's much more civilized. That's what we need. And so that's what 2110 says we have to do. But 2110, specifically 2110-21, which talks about the video timing, says there are actually different schedules. So depending on what the source device is trying to do, there are 3 different sender profiles that it could adhere to. And unfortunately, we do need to know a little bit about the details of those because this is one of the underlying causes of incompatibility between 2110 devices. So, 2110 sender types. The first sender type is a narrow or type N sender. And a narrow sender, within our frame period, it's going to look a little bit like baseband video in terms of the timing, which is to say that we are going to transmit a series of packets at nice regularly spaced intervals, but at the end of that frame period, there's going to be a bit of a gap, just in the same way that baseband video has vertical blanking. So we'll send our active video raster with the pixel data, and then at the end of the frame, there's going to be a pause before we move on to the next frame. So we call this a gapped packet read schedule. and it does effectively match SDI timing. Okay, second type then, a narrow linear sender, or a type NL sender. Now, over that same frame period, we still want to send the same amount of data, but this time we're not going to have a gap at the end, which means we can space our packets out a little bit more. So it looks something a bit more like this. And the advantage of doing this is that overall now we are dealing with a slightly lower bandwidth as we send that stream over the network. And that's helpful because it prevents us overwhelming the network. So we call this a linear packet read schedule. It does have a lower peak bandwidth, which is helpful in terms of managing the network. Okay, what's the third type? The third type is a wide sender, or a type W. And a wide sender is just a little bit more flexible in terms of what it does. And what that effectively means is that we're allowed more jitter in terms of the packet timing. So we don't have to have quite such a regular series of packets. Sometimes they'll be a bit closer together in time. Sometimes they'll be a bit further apart. So it's a less strict packet read schedule. The advantage of doing this is that it's a bit easier to transmit because the transmitter doesn't have to worry about getting that timing exactly right every time. And that's helpful if, for example, you're trying to do this in software where it's a bit more difficult to guarantee the packet timing compared to doing it in hardware. The downside of doing this is that, unfortunately, it's rather harder to receive. So 2110 gives the sender a choice. Are you a type N, NL, or a type W sender? Okay, so that's the sender side of things. What about receivers? Well, there are multiple types of receivers, but they don't map quite the way that you might expect onto the same N, NL, and W categories that we have for senders. So the first type of receiver we call a narrow synchronous receiver. And a narrow synchronous receiver is able to receive both a type N narrow stream or indeed an NL narrow linear stream. But unfortunately, it's not capable of receiving a stream from a wide sender. So this is a potential cause of incompatibilities between 2110 devices. If I have a wide sender, but I only have a narrow synchronous receiver, if I try and connect those together, it's either not going to work or it's not going to work reliably. So we should avoid that. If we do need to use a wide sender, we need to be looking for what we call a wide synchronous receiver, which is also able to receive narrow and narrow linear streams, but on top, it can now handle the stream from a wide sender. So this is a bit more difficult to implement in terms of the receiver, but you've now got broader compatibility with all three sender types. Now, both of these receivers are synchronous receivers. I haven't really talked about that yet. So synchronous receivers essentially mean that whichever type of sender we are trying to communicate with, we have to synchronize the sender and the receiver together. So this is a little bit like saying, actually, in the baseband world, everything's got to be gen-locked together, otherwise we're going to have some problems. A lot of the time, that's exactly what you want. But 2110 does also say, well, there is another type of receiver available, which is an asynchronous receiver. And an asynchronous receiver, again, is able to receive all three types of video stream. But this time round, you don't have to synchronize the sender and the receiver together, which sounds like it's a good thing, and perhaps it could be in some situations, but also have to be quite careful, because at the point where the sender and the receiver are not synchronized, this is a little bit like not using Genlock, you start perhaps seeing artifacts that you don't want. So you could see frame doubling, you could see frame dropping, that synchronization in terms of when the video frames are coming in and when we're actually able to work with them as a receiver, it's not there. So asynchronous receivers, part of the standard, but we need to be very careful because there are caveats there. On top of all of this then, we do want to talk a little bit about redundancy. And redundancy 2110 references 2022-7. And 2022-7 is all about how do I set up a network with multiple devices where actually a single point of failure on that network is not suddenly going to bring down my system. So within 2022-7, we basically say, okay, let's create two networks. So we're going to have both a primary network switch, but also a backup network switch. And every device is going to have two connections, one onto our primary network and one onto our backup network. Now, the point at which we then decide that we've got some data that we want to transmit, we are going to transmit that over both connections at the same time. Similarly, both of those connections are then used to forward that data on to our receiver. So the receiver can receive the data from one or the other or both of those networks. And it doesn't matter, because as long as it comes in on at least one of those connections, it's able to reconstruct that original stream. And this happens at a packet level. So if there are problems dropping a few packets on your primary network, and there are problems dropping a few different packets on your backup network, actually that's okay. 2022-7 will still be able to reconstruct the original stream. So that's really helpful. So, to recap then, we've said AV, data, timing, and this shared interpretation. Well, we've been talking about the data side of things here. How do we send that data over a network, or indeed over multiple networks for redundancy, from a sender to a receiver? Next, we're going to be looking at timing and how we do the same there to transmit timing over a network.